In our understanding, time feels like an independent, abstract concept with only one direction, flowing steadily from past to future. But have you ever wondered why? Why does time only move forward, not backward? Why can we recall the past, but not anticipate the future? Are we moving through time, or is time moving through us? To explore these questions, theoretical physicist Carlo Rovelli offers his perspective in his 2018 book, The Order of Time. Rovelli, a pioneer in loop quantum gravity theory, was named one of the world's 100 most influential global thinkers by Foreign Policy and is often called the new Stephen Hawking. In The Order of Time, he challenges our inherent view of time, proposing that time is an illusion shaped by our perception rather than by any absolute natural law. To explore the nature of time, let's first re-examine what time truly is. The most immediate sense we have of time suggests it has four main characteristics: independence, unity, presence, and direction. Let's begin with the independence of time. It's commonly thought that time flows on its own, unaffected by anything, and that nothing can stop it. This view originated with Newton. Newton proposed that time is absolutely independent, disconnected from everything in the external world, and he based modern physics on this concept of time. Today, we often accept this view as common sense, but it is actually Newton's personal interpretation. As early as the 4th century BCE, the ancient Greek philosopher Aristotle held a different view. He believed that time must exist alongside change. In other words, when we refer to time, we are really speaking about things in motion. For instance, if I'm on a 3-day business trip, those 3 days mean that the sun will rise and set 3 times between my departure and return. But if everything stayed completely unchanged, would time still pass? Aristotle's answer is no. If nothing changes, then time does not exist, because time is simply a record of change. If this is true, then why can we still feel time passing when we lie still in the dark? It's because your heart continues to beat, and your thoughts continue to shift. Even in stillness, the changes within you allow you to sense the passage of time. Another prominent figure who opposed Newton was Gottfried Wilhelm Leibniz, a German mathematician, philosopher, and physicist who lived at the same time as Newton. Leibniz believed that time could not exist independently. He argued that something more fundamental underlies time: causality. For example, when you pour beer into a glass, there are numerous causal relationships at play. If the beer bottle cap isn't opened, the beer cannot be poured out. If the beer isn't poured out, the glass won't be filled. By understanding these causal links, we can grasp the sequence in which events unfold. To Leibniz, time was like a chain of dominoes, with each event triggering the next in a series of cause and effect relationships. It is through experiencing the transmission of these relationships that we sense the passage of time. There is a legend that Leibniz once deliberately removed the letter T from his name to symbolize his opposition to Newton's idea of absolute time. But is time independent? Einstein made his judgment, which has since been widely accepted by the scientific community. He argued that time does not exist independently. Here's how he proved it. The first step was establishing the principle of the invariance of the speed of light. This means that regardless of whether you're standing still or traveling at high speed in a spaceship, the speed of light you observe remains the same. Additionally, it's impossible to exceed the speed of light. If it were, countless absurd scenarios could arise. For example, a victim dying before the murderer even fires a shot. This limitation ensures that causal relationships in the universe remain intact, indirectly supporting Leibniz's view. In the second step, Einstein proposed a new way of understanding space and time. He believed they are deeply interconnected, forming an inseparable unity. A simple example is the light year, which we use to measure astronomical distances. Here, we use time to describe distance, hinting at the connection between space and time. Together, they form what we call space-time. Einstein didn't just unify space and time, he also integrated gravity. For example, the sun's gravity keeps Earth in orbit around it, but in reality, it's the sun's enormous mass bending the surrounding space, with Earth simply moving along this curvature. So, gravity isn't a force in the traditional sense, as Newton described, but rather the effect of mass and energy on space-time. This curved space-time, shaped by an object's mass and energy, is what we call the gravitational field. The gravitational field is a physical entity that exists independently of us, yet it interacts deeply with the world around it. For example, in Newton's concept, time is like a stage, while life and matter in the universe are like actors on that stage. No matter what the actors do, the stage of time remains unchanged. However, in Einstein's view, the stage and the actors have a dynamic relationship. They influence each other continuously. In this way, time's independence is broken. So, how exactly does the stage of time perform with the actors? This brings us to the second characteristic of time, unity. We generally assume that time is uniform and the same for everyone and everything. However, the truth is quite different. Time is never truly fair. It fluctuates, sometimes fast and sometimes slow. According to the principle of time dilation in relativity, two main factors influence the flow of time, mass and speed. Let's start with mass. Objects slow down the flow of time around them. Massive objects distort the space and time around them, meaning the greater an object's mass or the closer you are to it, the more time slows down. For example, on Earth, people theoretically age slightly more slowly at sea level than at the top of a mountain. But if you live on a mountain, there's no need to worry or rush to move. The difference is so tiny, it's negligible. Now let's talk about speed. Movement also slows down time. The faster an object moves, the more time slows for it. For instance, time passes more slowly for someone on an airplane than for someone standing on the ground. Now we understand that the flow of time can be altered by both mass and speed. So, which of these is the real time? Carlo Rovelli suggests that there are many different times in this world, none more real than the others. This challenges the idea of time as a unified experience. But if two people experience time differently, how do they communicate across their different times? For instance, imagine you and your spouse are planning a trip. If the flow of time isn't unified for both of you, how would you carry on this discussion? This brings us to the third characteristic of time, presence, which refers to the sense of time's immediacy. A key concept closely related to presence is the now. Imagine you see someone in your family doing something, but keep in mind that you're seeing them because light is traveling from them to your eyes. Light takes time to travel, even if it's just a few nanoseconds, a few billionths of a second. So what you're actually seeing is what they were doing a few nanoseconds ago, not exactly now. But what if someone lives on Proxima Centauri 4 light years away? In that case, you would only see what they were doing 4 years ago. You might wonder, does what I see them doing 4 years later count as their now? The answer is no, because time is not uniform throughout the universe. The flow of time changes based on factors like the mass of surrounding objects and the relative speed of the reference frame you're in. So, trying to match a now on Earth with a now on Proxima Centauri doesn't really make sense. Not just on Proxima Centauri, but throughout the entire universe. There's no single, unified now. The concept of now only has meaning locally. How far the concept of now can extend depends on how precisely we measure time. If we measure time in nanoseconds, now would cover just a few meters. If we measure in milliseconds, now could extend to thousands of kilometers. So the concept of now is really a simplified idea based on our perception. However, what stands out most about time is its fourth characteristic, direction. For ages, countless people have lamented that time never returns. But why does time distinguish between the past and the future? Scientists in the 19th and 20th centuries explored this question, yet in physics, it is nearly impossible to find a law or equation that distinguishes between past and future. Whether it's Newton's mechanics, Maxwell's electromagnetism, Einstein's relativity, or quantum mechanics from Heisenberg and Schrödinger, all of these fields describe reversible phenomena. This means that if something can happen in a forward direction, it can also happen in reverse. So if this is the case, why do we say that one direction is the past and the other the future? Among the laws of physics, the only truly irreversible one is the second law of thermodynamics. This law describes the tendency for entropy to increase or stay constant in an isolated system, meaning natural processes are irreversible. Simply put, heat won't spontaneously flow from a colder to a hotter area, and a system's disorder will increase over time. What's particularly fascinating is that heat is deeply connected to the directionality of time. Anything that distinguishes the past from the future involves heat. Take, for example, an object falling to the ground. As it lands, its mechanical energy transforms into thermal energy, slightly warming the Earth. Once this heat disperses, the object comes to rest. Without heat, the object would keep bouncing endlessly, obeying the law of energy conservation. Similarly, we age because our bodies generate heat, and bicycles wear down because friction creates heat. Wherever you observe the passage of time, you'll find heat playing a role. Rovelli pointed out that the directionality of time mainly comes from the increase in entropy. Since heat only flows from high to low temperatures, we perceive this as the arrow of time. This isn't because time itself has an inherent direction, but because the phenomena we observe unfold in an irreversible way. In the vastness of the universe, our planet is tiny, so our perception of time's irreversibility may be just a small fragment of the larger cosmic order. For example, imagine an infinite sequence of numbers arranged randomly, where the numbers in our position are ordered from small to large. From our viewpoint, we might naturally assume that the entire series follows this order. But if we step back and view it from a higher perspective, this understanding clearly becomes inadequate. In fact, at the quantum level, the arrow of time doesn't exist as we experience it. One of the fundamental aspects of quantum theory is discreteness. This means that certain physical quantities, such as energy, angular momentum, and the charge of the electromagnetic field, can only take specific discrete values rather than arbitrary continuous ones. This phenomenon is known as quantization. So, what happens when time is quantized? Rovelli suggests that if time is quantized, it would appear in fragmented form, existing in the smallest possible units, rather than flowing continuously. That is, it would become difficult to determine with certainty whether an event has already occurred or will happen in the future. Simply put, at the microscopic level, time could even appear to flow backward. When time loses its independence, unity, presence, and direction, the time we're familiar with essentially ceases to exist. So, how does a world without time function? In 1967, American physicists John Archibald Wheeler and Bryce DeWitt proposed a crucial equation in quantum gravity, known as the Hamiltonian quantum gravity equation. One key feature of this equation is that it lacks the time variable. In this framework, time is no longer an independent variable. It disappears or is frozen. Initially, no one, not even the equation's creators, could fully grasp its meaning. Without time, does this imply a static, unchanging world? Later, it became clear that the absence of time in the equation doesn't mean the universe is static. Instead, it suggests that change happens universally, independent of time. The equation doesn't describe how things change over time, but how they change in relation to one another. Here's an example to help illustrate. Galileo discovered that the time for each swing of a chandelier could be measured by his pulse. Later, the pendulum was invented because its swing duration was fixed, allowing doctors to use it to measure a patient's pulse. Do you see the cycle? Galileo used his pulse to measure the pendulum, and doctors used the pendulum to measure the pulse. In essence, time is just an intermediary. In this sense, time is like a construction line in geometry. Though it doesn't exist in itself, it helps us solve the problem. If we find variables that synchronize, like the pendulum and pulse, we can use their mutual changes to represent time without isolating a specific quantity and naming it time. When we discard time as a concept, one thing becomes clear. The universe is made up of changing events. We once thought the universe was made up of objects, but in fact, all objects are simply events in motion. For example, a stone is not a solid object. It's a complex vibration of quantum fields. A cloud is not a thing, but the condensation of water vapor in the air. A family is not an object. It's a collection of relationships, events, and emotions. In this universe of ever-changing events, anything can play the role of time. This is how the universe truly operates. But if time doesn't exist, why do we feel its passage so intensely? Where does our perception of time come from? Rovelli suggests that time emerges from our memory. As mentioned earlier, heat plays the role of time, leading to an important consequence. It leaves traces. For instance, when we write, the friction of the pen slightly heats the paper, leaving a mark. Similarly, our brain collects traces from the past and transforms them into memories. The brain can also combine scattered memories to predict the future. For example, when someone throws something to you, your hand instinctively moves to where the object will be, based on a judgment formed from past experiences. The brain also creates continuity. Take the video you're watching right now. It's actually composed of many still images, but your brain seamlessly connects them. Time, in a similar way, is a continuous feeling constructed by our brain.